Chapter 18, the interstellar medium. Okay, so this is, things that are between the stars. When you think about a galaxy or even other galaxies, primarily we're talking about our galaxy right here. Later on, we'll extend this idea out to other galaxies. But, what's between the stars? Obviously, it's not just empty space. Well, not obviously. We didn't know that, actually, when we first started studying stars, hundreds of years ago. People assumed that there was nothing. And then, slowly, as we got more and more technology, we found that there are lots of things between the stars. This is... In general, astronomers a long time ago called objects like this these things were clearly not a star. It's not a single point of light, but an object that looks like this is called a nebula, and that just means like a hazy looking object. Right? So this is different than a star, right? Like these little obviously these little dots right here would be the stars, but this object is called a nebula. And by the way, it doesn't look like this to the naked eye, or even if you looked at it through a powerful telescope. A lot of these we use filters to enhance certain parts of the nebula so that we can find we can get information about them. Let me point out a couple of other things here. Notice these really dark streaks. That becomes really important in studying what is all out there between the stars. The interstellar, the stuff between the stars, the interstellar medium. All right, so let's get started. We'll talk about what's out there. These things called emission nebulas. The dark dust clouds, which is kind of what I was just talking about, these regions right here. How can we detect, where these dark clouds are? We use this thing called the 21 centimeter wavelength. Like this, and I'll get more into this in a little bit. These clouds you can see because there's, you can make it out because there's bright material around it or behind it. But what about dark clouds that are out there and there's nothing particularly bright behind it? How do we detect those regions of the galaxy? And so that there turns out to be this thing called the 21 centimeter wavelength. We'll go into that. It's a quantum mechanical phenomena when the electron and the electron and the proton and the hydrogen atom are spinning in the same direction, and then when they spin in opposite, kind of anti-parallel to each other, we'll look at some pictures of what that means. Anyhow, that allows us to map these regions of these dark clouds. Then, of course, there's interstellar molecules. What molecules exist between the stars? All right, so let's start off. This is just a huge, this is not one particular picture. This is many pictures put together of our galaxy, and so we're looking at, different parts of our galaxy, and notice there are regions that are particularly bright and then regions that are very, very dark, and so we're trying to understand those. And we realize that, of course, there are stars behind these dark regions, and perhaps there's something that's blocking the light. All right, so the interstellar medium consists of gas, primarily hydrogen, like atomic hydrogen, just a single hydrogen atom, and dust. Okay, so gas is, as I just said, the atoms, and sometimes there are some smaller molecules, like I said, most of it is atomic hydrogen, but there's a little bit of molecular hydrogen sometimes, where we call that H subscript 2. Where there's two hydrogen atoms bonded together. But mostly gas can be considered just hydrogen and helium, the two most abundant elements in the universe. what is dust? Okay, so we're we're talking about gas and dust. Dust is more like smoke, right, or soot. If you've ever been around the stuff that remains after there's been like a fire or something like that, like a campfire. So the larger molecules clump together and they form these particles, and that's really what the dust is all about. So the thing about dust is, and we can study this here on Earth, of course, that dust tends to absorb light. And it has that effect. And so what happens is, because of the wavelength, right? Recall, red light has a longer wavelength. So the red light that the human eye can see is 700 nanometers. The blue light that the human eye can see is 400 nanometers, right? So that's shorter. Dust will tend to redden the light. Basically, what that means is it's absorbing the blue light, and so the light that does get through it tends to be more towards the red end of the spectrum. So that's what we're talking about, reddening. This idea of reddening is very important when talking about interstellar matter. All right, and we can actually work out what the temperature of this material is, and we even see spectral lines, of course, and of course the reddening. Okay, so what's the reddening as opposed to the reddening that is caused by the Doppler shift, for example? Okay, so remember that there is this. We talk about the red shift or the blue shift. That is objects moving towards us or away from us. This reddening that we're talking about, if you have spectral lines, like there's certain absorptions that are taking place, or even emissions in some cases, as we'll get to emission nebula. Anyhow, the spectral lines don't shift. Right, so these lines are right where they would be in the laboratory. So that's the red. Would be the reddening that we're talking about, the absorption of the shorter wavelengths due to these clouds of gas and dust. But mostly the dust, right? The dust is the thing that does most of the absorption, but the gas does some as well. All right, so let's say you have, here's your telescope, and you have light passing through one of these dust clouds, and what you would normally, if the cloud wasn't there, there would be, let's assume the cloud's there, and it's, there are very few photons that can't get through. Even the blue light can get through. Okay, so it's very, very thin. You're going to have some absorption lines, because this is generally cooler than the starlight that passed, that's behind it. And so you'll get some absorption lines. But because if this cloud is dense enough to cause the blue light to be absorbed more than the red light, then what you do is you'll have the same spectral lines, right? Exactly the same spectral lines as we see down here, these absorption lines, but you're going from the black body curve, you're missing the blue end of the spectrum, right? And it's just because, of course, blue light has a smaller wavelength. All right, so here's some actual pictures down here of these dark regions, and we find these all throughout our galaxy, and we find these in other galaxies as well. So what is dust exactly? So there are various atoms that are in molecular form, and these things they're oddly shaped. You can have even there's even some like tiny organic molecules. Organic always implies that there's some kind of carbon involved. Like for example, one of the things we're going to see a little bit later is things like formaldehyde or carbon monoxide. You know, these are some of the interstellar dust that we're talking about. All right. So here's a nice region, and what we're going to talk about is what's called an emission nebula. Excuse me, an emission nebula, and so this is these. Oh, so let me go back to this for just a moment. See, sometimes you'll see regions of the sky, and you look at any star map, for example, they'll have these things called M numbers, right? There's about 100 of them, and they are from an astronomer a long time, more than, I think it was 200 years ago, a guy named Charles Messier. And Messier was a comet hunter, right? And he had a telescope, and he would look for comets. And so comets have the same appearance as these nebula, but what the difference, of course, is a comet is part of our solar system, so it's going to move over the course of just a few nights. You'll see it move with respect to the background of stars. These things that he named, M1, M2, and so forth, all the way up to about M100. These objects, the reason he numbered them is he wrote down, what their locations were, is so that, when he was looking for comets, when he came across these objects, he realized, just keep going. These are not comets. They're in the exact same spot in the night sky, night after night after night, and throughout the entire year, right? So that's really what they, and it was actually one of the very first catalogs. There's many other catalogs now. This is a very popular one, the NGC, the New Galactic Catalog, as it was called. I don't know, it's not very new, not now anyway. But so like I said, sometimes you'll see these Messier objects. Like, for example, I mean, you know some of them, like as you watch, if you know the night sky, like this is this one right here is known as M42. Anyhow. All right. So the nebula is, as I said, just this fuzzy region. You can have dark nebula, and you can have a very bright nebula, which it turns out that there are really, really bright stars that are emitting light inside of these emission nebula. Let's see what else. And there's also even what are called reflection nebula, where there's light that is bouncing around inside of these nebula, and then gets reflected in the direction of our telescopes, of course. Let's see. Some of them have names. I mean, like this one in the middle here is called the Trifid Nebula. Or I'm sorry, this is the Eagle Nebula. Yeah. Anyhow, that's not that important. So the emission lines that we see are generally red, and that is because of the H alpha line. Just to remind you this from chapter 4, the H alpha is the transition in a hydrogen atom, so it's an atom, not a hydrogen molecule, between the N equals 3 and the N equals 3 state, the energetic electron in the N equals 3 state, dropping down to the N equals 2 state, and that's a red line. You might remember this or you might have seen this in laboratory when we saw the red line for hydrogen. All right. Anyhow, we also see these dust lanes. Here, let's take a look at that. So this right here and in here, There's these very, very bright nebula, but